Hello. In this video, I will show you how to solve the domain and range for absolute value graphs. Now, this is just one of the many ways to actually sketch these graphs, and they are actually more than just the way that I show you. So, for these kind of graphs, usually if you have an absolute value function and maybe toss in a negative coefficient in the front, plus or minus constant afterwards, it can write this in the form y equals a absolute value of x, maybe in terms of a linear, plus a vertical translation. So what we can do first is to see when is the inside going to be at 0. That will determine the cusp, so where the V shape is going to be having the turning point in a way. So for the first question, well, x is 0 when x is 0. That means it's going to be right in the origin. Now the next thing we want to do is to determine if it points up or down, and the hint is in the negative. So that means we have a point that's going to occur at the y-axis, but because of the vertical translation, we know that the curve starts over at 0, 3. You could also use table of values to give you a few points and see what the curve looks like, but in any case, the V-shaped curve should look like this. This will be a 45-degree angle since the coefficient of the absolute value function is just 1. So if I want to give it the scaling, this graph would just have a 1-to-1 scale. So if I want to be really precise, then I will attach arrowheads to represent that they actually keep on going forever. So as you can see, the domain is going to be all real numbers, whereas the range is anything less than or equal to 3. And of course, y will be in the set of real numbers as well. Next one. So if I solve for the inside, again, we have this to be a 0. Now this time it's a little bit different though. If I want to write it in this form here, then I can actually just write this as two absolute value of x minus 1, right? So therefore, we have it starting at 1, negative 1, sorry. And it's going to change by 2 because of this coefficient here. That means for every step to the right, I'm going to go up twice. So you can think of it having a gradient of 2. And it's going to open up this way. I'm still going to maintain the 1-to-1 scale. So if you compare this curve to the last one, this one is a bit sharper. So then the domain is going to be all real numbers. Here we have a minimum. So y could be anything greater than or equal to minus 1. Okay, so here, if I set the inside to be 0, we have x equal to 3. So that tells us that at x equals 3, we have a turning point, in a sense. But that turning point actually occurs at minus 4 as well too. So together with 3 and minus 4, we have this vertex over here. And again, we're going to have a 45-degree line. So it might look like this. Still 1-to-1 scale. So what is the domain? All real numbers. And the range will be anything greater than or equal to minus 4. So if I look at the inside, it's 0 when x is equal to 2, when x equal to 2, So that means the vertex is going to have this coordinate for the x value. And we have a vertical translation of 1. And this time, because this is a negative, we know it's going to point downwards. So it's going to point down at 45 degrees. And we still have our 1-to-1 scale. Domain, you should know by now, it's all real numbers. And y in this case is anything less than or equal to +1. Here. So we can set the inside equal to 0 first. So there is going to be -2 for the x coordinate, -1 for the y, so that's the vertex. This time it has a scale factor of half. So that means every time I go up, I go right twice, I go up once. So 2 right, 1 up, 2 right, 1 up. And in the other direction, 2 left, 1 up, 2 left, 1 up. So our domain, all real numbers. Y is anything greater than or equal to -1. Okay, so a couple ways of doing this. You can find out what the sort of like the axis of symmetry. So it's at -2. But if you plot it, we have to sort of find out what the gradient or what the scale is going to be. So we can actually rewrite this as that. So if you take out the 3 as a factor, but what comes out still stays positive. So technically, if you set the absolute value to 0, you get x equals to -2 again. But in any case, our vertex will be at -2, +2. And this time it has a scale factor of -6. So that means as I go one step to the right, one step at a time, it's going to go down by 6. So if I use a 1-to-1 scale, you will only see that this goes from 2 to -4. And then I can't even go further. So I will just connect this. If only I have if only I have a ruler. Oh, come on. Let me shrink it down a little bit. Maybe it'll be easier. So our domain is all real numbers. And our range in this case will be anything less than or equal to +2. Okay, so here, what I'm going to do first is I'm going to take away a -1 from the absolute sign so that the inside has a positive x term. Now, the neat thing about this is when you take away a -1 from absolute value, actually it still becomes a 1 on the outside. So these are actually the same graph. So then, when is that 0? When x equals 1. And it will have a vertex at 1, 2. And this time you have a -3, so it means that it's going to go down. And the ratio is every one step to the right is 3 down. And by symmetry, so again, we just have a 1-to-1 scale grid, which is rather nice. Let's go up and complete the domain. All real numbers. Range will be anything less than or equal to +2. So now that you know how to do 7, question 8 is pretty much the same. I'm going to do two things at the same time. I'll take away the negative as well as the common factor. So this will become that after the first step. Okay, so that's that. Which means we have the vertex at 3, -2. The scale factor is -3, so that means it's going to point down with a gradient of 3 pointing downwards. So in other words, you can think of it as a negative gradient of -3. So that means the next point should be here and here. Ooh. So the domain, again, is all real numbers. And the range is anything less than or equal to -2. I may have said X, but I meant Y. Okay, last two questions is a bit odd because you have a quadratic. So for these questions, it's probably best if you think of this as graphing the quadratic and then flipping anything that's below the quadratic back up to the positive. That's probably the easiest way to visualize and actually graph in this case. So if I factorize the inside, I will have -1 + 3. I'll have this. So that means I know that x is going to be 0 at these 2 points. Now these are going to be critical because they tell us when the graph is going to be below the x-axis. So if I put in these 2 points, this is roughly there and here. So originally, the quadratic curve inside the absolute value is opening upwards because it's leading by 2x squared. 2 is positive in this case. So I'm going to draw the quadratic. So this is what the quadratic will look like, the green curve. It may look like this. Now it's not quite accurate because I don't know what exactly the minimum point it's returning. Okay, so this might be the original curve. And with the absolute value curve, what it does is it takes the positive, it keeps the positive. Okay, it keeps the positive part, but it mirrors. So this is, if I'm going to use this graph, actually, I know the midpoint because this axial symmetry has to happen at the midpoint. Let's get a better approximation. This is a sketch anyway, so you don't have to really have to do that. At least how about I do what 0 has to be. So when x equal to 0, we have -3. So maybe if I redraw the curve so that it at least reflect that point. So I need this to go to -3 originally, okay? This is the original curve, so it's not really the true part of the curve. Okay, something that looks like this. So if I want to actually sketch the absolute curve, this should go up to 3. Okay, so it's the red part of the curve. So imagine if you like take away the green curve. Okay, it's kind of like this W shape there. Now, if we use calculus, we can actually find out where this point is. Or if you know a little bit about quadratic, for example, changing it to vertex form and finding the minimum for the original curve, that would become the maximum for the absolute value curve there. Or you can simply differentiate and set the derivative 0. But again, this is a sketch. I think the most important thing is to be able to recognize that this curve will have a W shape. Now, so the domain, it's still all real numbers. In that case, if you collect everything, the range is just anything that is 0 or above. And similarly, so I'm going to first of all take away the negative. So factor a -1 so that everything inside it's going to be leading by a positive coefficient. So I could technically just write down this line here, but just to show you what the process is. And factor it. It should be 2 and 3. Nope. It should be -3 here and +2 here. You determine what they are. This will give us an idea of what the curve looks like. But this time we are shifting this up by 2. Okay, so this one is a little bit more difficult because we're not sure if it actually goes below that 0 line. Because if we just consider the quadratic, it's going to, okay, let's write down the roots here. -2/5 around here, and 3. So the curve originally may look something like that, right? But then we want to shift it up by 2 units. Okay, we want to shift this up by 2 units, so it might look like that, right? But we don't exactly know the effect, to what degree the effect actually shift these roots as well too, right? Because that should be the curve, right? The purple curve. So because this is a sketch, this is probably the best that you can do, unless you do table of values, okay? If you do table of values, maybe you will have a more precise curve as to what those numbers are going to be. But exercise here, we will just leave the question as this, and the range we actually have to use calculus to determine it. Okay, so hope you guys learned something, and I'll see you in my next video.